And first of all, thank you, Professor Alexi, for giving me this opportunity. Today, we are going to talk about CompuCache, a paper essentially from Microsoft. It is a cloud service built for Spot virtual machines to utilize the unused memory locations that we have in the data centers. And if you consider any data management systems, it deals with a lot of data. And to do certain computations inside the data with low latency, it requires a lot of main memory. But as we all know, memory is so expensive. Companies such as Google, Alibaba, and Facebook shows that their memory utilization across their data centers is below 50%. And a small experiment conducted by this paper says that their they took 100 compute clusters and tested it over a 100-day period, and their results show that almost 23% of their memory, the memory of a single each machine, is unallocated, and also a median of 43% of all the machines are memory free. So this paper aims to use those kind of memories that are not used for computation purposes in these large data management systems. And there are such experiments such as using Spot instances, but I mean, basically Spot instances are like tiny virtual machines created on top of those unused memory locations, and but they are really temporary. So the application must be ready for losing that particular Spot instance on a short notice. But there are some struggles around using Spot instances if they are not handled properly. So this paper is building a service around those Spot instances so that they can be used in an effective way. For example, they are using these stored procedures instead of using normal commands like normal read or write commands to the system. Like they are using stored procedures, which we'll talk about later. And they are mainly focusing on using these caches or memory locations in a very inexpensive way. So for example, the stored procedures they're talking about is nothing but a set of instructions to the system. For example, if a client wants to sum two values, it needs to read A, and then it needs to read B, and then it can say that, okay, I have A and B, and now sum it together and give me the result, which is really taking a lot of round trips compared to if you give a stored procedure having all these instructions inside, and that particular server, if it doesn't have any data, it can actually contact the server that has the data and finally get the result to the client. So this is a typical generic example of how a stored procedure could work. And as you can see that the number of round trips are really less compared to the normal way. And they're given a design of how this CompuCache is going to work. Is like it has a client, a CompuCache client, which talks to a cloud VM allocator whenever it requires a certain cache for a particular computation. And we have these Spot instances called CC server virtual machines, which are built on top of this Spot virtual machine. I mean, built on top of these memory locations that are not used. So each and every server could perform certain commands or implement some methods. For example, if you take CC client, it could actually ask a cache location, like a cache memory, to the cloud VM allocator using allocate method. And then when it don't want a certain cache location, it can actually say release that particular memory that it allocated before. And the cloud VM allocator, once it received the allocate method from CC client, it will actually look through all the Spot instances it has and see if it can allocate any of the existing allocate memory from existing Spot instances. If not, it will actually try to reclaim one of them to see if any of the Spot instances are no longer used. If it couldn't even provide that, then it can actually provision a new VM, but eventually that new VM's data will also be transferred to this existing Spot VMs for cost efficiency. And as you can see, each server machine can communicate with other server machine using these particular commands, dflow, fflow, and migrate. It is essentially to transfer data across them, just in case if a cache is allocated and then client is requesting some data, it didn't have that entire data, then it can communicate with the other server, which may have the remaining data, and then get back to the client. And CC client also has the ability to maintain a mapper. For example, whenever a CC client says to the Cloud VM allocator, I need this much memory or in these many cores, then Cloud VM will see and allocate either one particular machine that satisfies all the needs, or it can spread across the VMs and say, okay, this is the list of VMs that satisfies your needs for this particular computation. And based on that list, the CC client will actually map the cache, the virtual addresses with the physical addresses, so that it can sync that mapping information to all these servers so that they'll be able to communicate among themselves. And when they are trying to communicate between servers, so like we said, like each server has the mapping information of how many servers are there, or if a client is saying like, go to this particular address or something, the server one could easily figure out like where that is located and communicate with it with the help of that mapping information. And also, enable to efficiently provide that, they are using this local data structure, local translator data structure, which is having this translate function. And in this translate function, they are actually seeing if the cache address and cache size that is provided by the client is, when it is assigned to a server, it is matching with their local address and size to see if the entire computation can be done in single server or not. If it is done in single server, then the server will say, okay, I can do it all by myself. I don't need to communicate with another server. But if not, it has to raise an exception. And the way they are handling these exceptions are 3 types. For example, if it wants to decide like, okay, I have only some information and I know that the remaining information is in server 2, then it can actually ask server 2 and get that information to server 1 using the flow method. If it decides to execute the entire, like shift the execution state entirely to server 2, it can use the flow method to actually bring the whole execution to server 2, and then the server 2 will be responsible to reply to the client once everything is done. And the response sizes could vary because if you are performing a simple read or write, you know the size of the response. But if you are giving a request saying that, okay, I need to know the aggregated information of something, and then the server might have to contact a bunch of other servers and then give the aggregated result back to the client, which will result in different times of these requests and responses. So one solution they are providing in the paper is using this ERPC library, which will use these network interface cards to make the network protocol faster, so that each and every result is batched into some size, and the size will be fixed dynamically, and then depending on that particular aggregated result, and then that batched result will be given to the client. And to be able to effectively manage those requests, since each client could give so many requests at the same time to a particular server, they are having a queue type data structure to hold those requests in a queue, and then this work queue will be actually giving each request like one by one to the server, and the server one by one to the server on that core. And since this is multi-threaded, so each thread will be given one request at a time, and hence no interjunction between requests happens. And when the Cloud VM allocator is trying to see what Spot instance it can reclaim, it will actually decide on one particular server. For example, server 1. The server 1 has the all the information, but it has to reclaim it. So now it has to transfer the information in that server to a new server and then start using this old server. But it is not as simple as that, because they have to take care of some points that can affect this, that can affect the efficiency. For example, in order to effectively migrate the data from one server to another server, keeping in mind all the reads and writes that it could get at every time, like every second, to that particular server, first the new VM will be generated, like created, and then all the data in the server one or the data will be migrated to server two, region by region. For example, this memory location to this memory location will be one region, and then will be transferred to server two, and then client will do the mapping. Okay, now client knows that server two has this region, so it updates its mapper, and then same happens until it reaches, like it is done with all the regions, and finally server two will have all the information, and eventually the server one will not be disabled at that point, but eventually will direct all the eventually it will not get any requests regarding the data, because now the server 2 is having that kind of data and server 1 can be used for that current computation. And a couple of points to note here is, like, when a server is migrating one particular region from one location, like server to another server, then a server or some client can actually try to access that region, thinking that their local mapping shows that that particular region is located in server 1, and then could try to reach out to that location. And server 1 will have this predefined tombstone, they say, that directs the addressing of that particular region to server 2's region's address, so that server 3 can actually get directed to server 2 directly when it is trying to access that region that is already migrated. And then server 2 responds to the server 3, and then at server 3, the server 3 will know, like, okay, now the local mapping is, I need to update my local mapping, and then it does accordingly. And typically in real time scenario, this notification from VM allocator is about 30 to 120 seconds, that it will tell the other, like it will tell the client that a particular server is about to be claimed, and then the reclamation happens. And there are also certain scenarios where servers could fail, and typically, like, overall the solution is like use some persistent data or persistent storage to actually save your data before, if in case of any crash failures. And the paper assumes that it is more inclined to these reclamation failures instead of server failures. And coming to evaluations, they compared it with Redis. And the first evaluation is cache over performance, where they are reading and writing 8-byte records with increasing number of threads. If you can see here, like the Redis is about 0.2 million operations per second on an average at one thread, compared to CompuCache, which is almost like 10 million operations per second, which is like 200 times higher throughput than the Redis framework. And the second evaluation is about the store procedure. So here they are trying to read a record, which is basically a store procedure, and then verifying its data if it is correct. So here the throughput is as you can see that the Redis throughput is slightly increasing and then getting saturated almost at 16 threads, whereas the CompuCache throughput is increasing as the number of threads are increasing, because each thread could hold a computation at a time. So the reason why Redis is not that effective here is the paper claims that it is because of the Lua script, and its runtime is not concurrent. So that affected the throughput of Redis a lot. And here is an evaluation about cache migration, which is nothing but the Spot reclamation. So they have execution times for client to server connection, server to server connection, and buffer allocation, and then the final region migration, which is transferring data. So the reason why they had buffer allocation is that when they're trying to transfer data from one server to another server, from the old server, they try to store the data in a buffer of that region, and then transfer that information into a buffer of the new server. And then the new server is responsible to save that buffer information into its local state. So they just decided like to remove this buffer allocation and do the rest, which actually increased their through execution times by like 1.9 times. So then they didn't have like then they are trying to actually migrate data directly from one memory address to another memory address without having this intermediate buffer allocation. So this is a general idea of what CompuCache is and its challenges during the implementation. And more details could be found in the paper. And thank you.